I said most of the Python standard library. So let's talk just for a minute about what isn't there. So some modules just don't make sense to have without an operating system. For example, we don't have exec or fork from the OS module because we don't have separately runnable programs or multi-process operation or a scheduler for that matter. So that then means we don't have things like multiprocessing, popen2, subprocess, or the all-important web browser module, which sadly means that you cannot import anti-gravity. Sorry. However, we also, when we were originally looking at some of these modules and thinking what makes sense to have in an operating system, we took a look at things like socket and select and the modules built on top of those like urlib2, httplib, socket server, or base HTTP server. And I remember very distinctly looking at these in the early days of bits and thinking, oh, we're never going to support that, right? So it turns out EFI actually has networking protocols. So when we moved up to EFI, we started thinking it really does make sense to have networking support. And why would you actually want to have this? Well, it turns out it's really convenient for sending scripts or test data into the machine you're testing, or for reading test data or test logs back out of the machine when you're done. Quite often it's more reliable than the local storage on the system, which you sometimes don't even have local writable storage. So it helps you avoid relying on a writable file system. So with that, I'd like to give a demo to kick things off. So one thing I'd like to point out all throughout this demo is that I'm actually giving all of these slides from inside the emulated environment. This was the big reveal on last year's talk, but I've got other interesting things to reveal this time, so I'll go ahead and hand that one over right now. But I am switching back and forth between that and a terminal. So let me first go run a web server from outside the environment on my local system. If you haven't used simple HTTP server, I highly recommend it. Just serves up the current directory with a web server. Great way to move files around quickly. And then let me go over to a prompt here. So just to prove that we're inside the emulated environment. And let's pull in urlib2. I'm going to print urlib2 urlopen of the web server that I just started and pull down a file. So it's going to take a moment to DHCP for an address inside the virtual machine, and as soon as it was done, it pulled in a file and printed hello world from outside the VM. If I run that again, it already has an IP address, so it can just instantly fetch that. If I go back and check my web server, it tells me, hey, I just tried to pull down hello twice. So there's the quick demo. So let's go back to the slides for a moment and talk a little bit about how this was done. So what we want to do here is to bridge EFI networking with the Python sockets interface. What we could do, in theory, pretty easily, is go call the EFI networking modules and protocols directly. We have all the Python code to call an arbitrary interface, and we could just write EFI-specific code. The problem with that is we really want to run existing Python networking code, urlib2 or an HTTP server, or who knows, maybe someday we'll run Django in the inside your firmware. BIOS as a service. So given that compatibility, we need to implement the same interface Python's modules expect for networking. So that means the socket module and the select module. And socket, which is implemented in Python in the standard library, we're actually using unmodified. We pull in the underscore socket module, which provides the low-level implementation. If you saw the presentation earlier today on file descriptors, then some of this will be familiar, but I do want to give an overview of sockets for anybody who hasn't used low-level network programming on a POSIX or Unix system before. So the traditional sockets layer is called Berkeley sockets. It's where it was written and originally devised. It's standard on Unix and POSIX systems, including Linux, OS X, pretty much everything else, and it's available on Windows via WinSock. So if you're doing network connections, this is probably what you're using. And I'm going to be focusing exclusively here on standard TCP/IP networking and not all the other fun things that you can do with Berkeley sockets. So let's start with, how do you create a socket in C? So you'd call the socket function to get a file descriptor, and you tell it I want IP with TCP inside of it, And the 0 here is the default way of doing that. So now that you have a socket, you can set that up to either be the client or the server of your connection. So if you're going to set it up as a client, that's the somewhat easier approach. You call socket as before, then you call connect and tell it, here is the address I want to connect to. And I'm not giving the full C code for how to do that, because if you're at all familiar with Berkeley sockets, you may have seen struct sock adder, which is one of the standard examples for how not to build a C API. So once you've connected your socket, then you can send and receive data. You can also use just read and write if you're on a Unix system. And then you close it when you're done. So a server is a little bit more complicated because you want to handle multiple clients. So instead, you bind to an address and say, this is the address I want to listen on and the port I want to listen on. Then that brings in our friend struct sock adder again. You listen on the socket and say, OK, I want to accept and queue this many connections until I start saying, sorry, server's all full. You call accept whenever you've got a socket ready to bring in, and that gives you a new socket, a separate file descriptor that you can then read and write, send and receive to talk to the client. And then when you're done with that one, you close it, but you can call accept multiple times in a loop. And this is pretty well much the standard approach that you'd see in a web server, an email server, any kind of networked server. So the other thing that we need to talk about is, how do you actually know? I kind of glossed over there. You call accept when you have a connection ready to accept. How would you know? You could just call it and block until you have one, but you can actually ask the system, is there a connection ready or is there data ready? You pass a set of file descriptors, and then I'm going to gloss over some of the more unusual things you can do with select, but you can give it a timeout as well. And what it will do is wait for a connected socket to have data to receive or to send, or alternatively wait for a listening socket to have a connection ready to accept. So when that happens, or if the timeout happens, it will return that back out. So select is actually the core of the main loop in the majority of network servers out there, either select itself or one of the more advanced OS-specific replacements like epoll or KQ or any number of other mechanisms to make this more scalable. But the core of most network servers is, I have a giant pile of sockets. Which of them can I do something with right now? So that's the C interface. Let's talk a little bit about the Python bindings to that interface, which are straightforward enough that I'm actually going to include sample code. So you can pull in the socket and select modules. The equivalent of calling the socket function is just socket.socket. And because TCP/IP is what you almost always want to use, either that or UDP/IP, the defaults are TCP/IP. You just create a socket. That actually gives you an object. And then from that object, you can call connect. You can call bind, listen, or accept, the same as before. And you can call send all and receive. Send all is just a wrapper around send that says, if I didn't send it all the first time, keep trying until I do. And you can call select. So the specific detail here is, given this socket in the read position of select, wait for some amount of time. In this case, it will keep waiting until you have data. Give me back the lists of what things that are ready. Since I only provided one thing, then it will just wait until that socket is ready to read or ready to accept something on. So then let's talk about how CPython does this. So these functions are all provided by the native C library on your platform. So they're implemented in C, and so are the CPython modules that interface to them. So there's a socket module that implements _socket, and a select module that implements select. So these have a very extensive dependency on POSIX and on the C sockets API. And that means we would have to go implement all of those APIs in C in our standalone pre-OS environment. And the less C code that I can write, the happier I am. So this isn't a very appealing proposition, especially because not only would we have to handle C arguments, C addresses, C buffer management, struct sock adder, but we'd also have to call EFI protocols from C, which we're actually not doing anywhere else in our code. We've written all of that in Python. So what we've done instead is, or we could call back from C into Python from that module every time we want to do one of these operations, which is a lot of ugly glue we don't want to write. But these are just two modules, underscore socket and select. So we could just write those in Python. So we have less C code. We have a tiny C helper that's needed to do asynchronous event handling in a safe, race-free way. And otherwise, the entire code is all Python. And then all of the EFI protocol calls for networking are all done via Python. So let's talk for a little bit, first of all, about how you actually call EFI from Python using ctypes. So I'm going to give a quick demo that is not networking related, that's instead just a test to do hello world. So let's pull in the EFI module. I'm going to go out to the system table, the console out interface, which is a simple text interface. Then I'm going to output a string, pass a this pointer because it's a C++ style interface, print the string with crlf because EFI is very DOS and Windows-like, and I get a greeting from my firmware. So there's a lot of stuff I'm glossing over here. Behind the scenes, there's actually a full data structure for a system table that has all sorts of things like who made your firmware, this is an emulated system, what your input and output protocols are, and some services that let you go pull in other interfaces. And then the simple text output protocol I grabbed is an interface that gives you functions like write out a string, reset the display, clear the screen, move where the cursor is. So these are all functions that you can call from Python. And we have a wrapper, this protocol type, that gives you all of these as functions in ctypes format. So that's the interface we're using to call these individual networking objects. And based off of that, we can call some more advanced mechanisms like the TCP protocol or the IP configuration protocol. So let's talk, I mentioned behind the scenes, you have a data structure, you have a pointer to a protocol. .contents here is just the ctypes way of saying the star to dereference a pointer. And most things wanted this pointer, we convert to, the ctypes actually does automatic conversions here, which is really handy. We don't have to go create a UTF-16 Unicode buffer, we just pass a string. And the 0 we got back after the hello world is just a successful return code from EFI. So some of the quirks that come up here is, even though this is Python, the EFI calls we're making underneath actually use manual memory management. If you allocate a resource, then you have to free it when you're done with it. We can wrap that in an object to do that for you, but it's not integrated with Python's garbage collector. It doesn't know also about references from EFI. So if we make an object and hand a pointer to that object into EFI, and then that object goes away due to garbage collection, EFI is going to be very unhappy, generally to the tune of a crash and reboot. So we have to keep Python objects alive as long as EFI is referencing them, and we've got some frameworks to help with that. The other is we do have to explicitly free EFI resources when we're done with them. So let's talk a little bit about the EFI protocols we're going to be calling. We've got IP4 config2 protocol, which is how the DHCP happened. You saw when I did erlib2 that it first went out and took a moment to call the DHCP server and get an address. That's how you do this. You can set a static address or use DHCP. There's the TCP4 service binding protocol, which is a protocol to go give you a new socket. So this is this is more the interface you use to get into the sockets layer. Then you ask for an object that is the actual socket, similar to a file descriptor. And then you have TCP4 protocol, which represents a socket. That has methods for configure, connect, accept, transmit and receive, and so on. And I'm glossing over a lot here in terms of quirks, bugs in the interface, error handling code, some of the workarounds for bugs in the interface, and older versions of these interfaces. But the actual code does include all of that compatibility. So the problem here is that we're talking about a socket interface and then an EFI network interface that actually have two entirely different models, not just new names for functions, but different models for how they handle things. So the first one here is that select in a POSIX system waits and checks until you have a pending connection or pending data. It doesn't actually read the data or accept the connection. In EFI, you call this function, which has a callback, and you have to give a buffer to it. And the way it tells you there's data is it says, here's the data, so you'd better be ready to have it. So at that point, we have to buffer the data that we receive, and we only actually call the underlying receive function when our buffer is empty. So this isn't too difficult to deal with. This is one of the easier problems to solve. Same thing for accept. And it's very similar to the actual implementation of sockets inside your OS kernel. As much as you'd like to call select from the user space side of things, the kernel has to accept data whenever it's thrown at it or tell the other end, sorry, I'm all full up, wait around a while. So that's fine. Another interesting one is this is a low-level firmware interface. There isn't a lot of background processing going on. It does process interrupts, but it doesn't necessarily pull the data off the minute that those interrupts happen. So the data is processed fairly infrequently via a background timer. Even if you have one of these asynchronous calls running, it doesn't sit there in busy loop. It lets you do what you're trying to do, so it doesn't break what you're doing in the foreground. That's its primary assumption is you're doing something else while you're waiting for the network. So you're expected to call this function poll. This is unrelated to the POSIX poll function that's a variant on select. This is go busy loop on the network and make sure I don't have any packets ready to process. If you don't call this, you get very poor network performance. So inside of all of our helpers that implement select, we end up calling this function whenever we're waiting around and have nothing better to do. And the last one that's really a challenge to deal with is that every call in the EFI layer is asynchronous. So if you want to do a blocking read because you have nothing better to do than wait for a web server connection or you're downloading a file via urlib2, then you need some way to block. On top of that, the mechanism for being asynchronous is that you pass in a structure which includes an event that gets signaled when you're done. The event gets signaled by calling a callback function, which is, of course, an EFI C API function. So we have to handle that callback safely from Python. So Python's concurrency model is kind of interesting. It expects every bytecode operation you run or every C call you make to run to completion before it's done. There's another talk here at PyCon about the global interpreter lock that helps enforce that. And if you break that model, if you go call a random callback function, you may have inconsistent state when your callback occurs. And that's going to break a whole ton of things. So you can't call pretty much any CPython function from this callback. The same thing happens when you hit Control-C on an interpreter. You take an asynchronous signal. That signal can't call an arbitrary function to raise an exception. What it does do is register a callback in Python using this function py_add_pending_call. This is part of the CPython API. And what it says is at the next point, when you're between bytecode instructions, not in the middle of C code, go call this function for me. And you can, from that function, call anything you could in the context of the main thread of the interpreter. So if we want to handle EFI events then, we provide a function pointer from C exported from our EFI module that gives you this callback function. The only thing this function does is call a registered global Python callback to do all the real work. And that callback goes and looks up the event in a dictionary, dispatches to a function, and then that dictionary also keeps all these objects alive while the event is referencing them, so you don't call off into the middle of something that has no purpose other than being called back. So with that in mind, how do we implement select? So we need to take a read and a write list full of sockets, or file descriptors. We have a mapping of small integers back to sockets. We loop over them until our timeout expires. We don't have a scheduler, and we literally do have nothing better to do, so we busy loop. We call a function on our socket implementation, read ready or write ready. And then the read ready function will say, do I already have data queued? And if I don't have any data queued, then go make the actual receive or accept function and have it running in the background so that data will show up. If I do already have some data, then I just immediately say, yes. If I'm waiting on a previous call, I call poll. If I have data queued, I say, yes, I'm ready. And if the connection's closed, you also need to say, I'm ready to give you an EOF. And if you call write ready, that one's a lot simpler. We don't want to maintain our own queue separate from the firmware, so we just say, yes, try writing, see if it works. And that just always calls poll. So now we can build a wrapper around this. We build socket. So we create the EFI TCP4 protocol. When we're done with it, we close it, and there's a function to cancel all the outstanding callbacks so that we don't call into freed memory. When we connect, we do configuration of the socket and then establish the connection. It's a two-phase process in EFI. When we receive, that's the same thing that we were talking about. Run the queue, receive data out of it. Send all, we'll call transmit and then save the status for later retrieval. Bind will save the address and port you give it. There's no call for this in the actual API, so you just save it off till you call configure. Listen will call configure and set it up with the flags for a listening socket. And accept will give you your queued connection. So we've written all of these in Python instead of in C and call into the underlying interfaces. So with that, I'd like to take the rest of the time and give a demo of how the socket interface works. So I'm still running this web server on the outside. So I gave the demo earlier for reading hello world, but let me try doing something a little at lower level. Let me import the underlying socket and select modules and create a socket, connect the socket, and let's do HTTP by hand. So then I can receive a packet for some reasonable default buffer size. Same thing, low-level HTTP via sockets. So let's take a closer look at what that's doing. Let's reinitialize a new socket. Let's connect and resend that. But instead of receiving all the data at once, let's take a look at that queue I was telling you about. So the queue's empty right now because even though you've sent data, we haven't waited to receive data yet. But if I call receive and just receive 1 byte, then there's the first byte of my data. And at this point, the queue actually has the remaining 12 bytes of data queued up. And I can look at that low-level object, and there's the rest of my string. But it's not actually received yet. I can receive the next byte, and the queue has gone down to 11 bytes at that point. And then finally, I can receive the rest of the data. So this is abstracting over that EFI interface, dealing with the queuing and slicing the buffer differently, and also avoids, if you want to read bytes 1 byte at a time, this will buffer a reasonable amount of that data, whatever the firmware gives you back. So on the other hand, let's build a server. So let's go back and do a socket again. This time, let's call bind. Listen for everything. Doesn't really matter how many connections I ask it to wait for. And I'm not going to go through the same queue mechanism again for accept, but I'm going to show how this mechanism works to call select. So I want to wait for there to be any activity on this socket, something I can accept. So that actually blocks, and it will keep blocking until, let me close this server, and instead do so now I'm connected, and that returned. So now I can accept that. I can see what connected to me, and then grab some data. And again, this blocks because I haven't sent any data yet. And let me send the data right back with something useful done to it. So communicating inside and outside of this VM using the network stack. So that's the low-level interface. Now let's talk about the high level. So I already showed off using erlib2 to do a simple hello world, but let's do something a little bit more interesting. First of all, let me grab the script that I'm about to use. Oh, helps if my server's running. So yes, we have error handling. So this is the script I'm about to run from the outside. This is a different server that actually accepts posts. Well, I could run that script on the outside and send data outbound, but I've already shown how to do an outbound connection, and that's just erlib2 doing a post. Why don't I do it the other way? I've just pulled in a script that doesn't exist inside my virtual machine. Rather than retyping it, let's run a server. So let's connect to that server. So let's go connect to and we'll pass some test data. Test data. So this is useful if you wanted to build an API. This script has a do post handler that's very trivial. You could easily make this read and write registers, retrieve large logs, or even build an interactive read eval print loop if you were willing to slap a little bit of JavaScript and forms on top of it. And we're actually seriously thinking about doing that because we have systems that are much easier to interface via the network than they are to interface via a console. So that's an example of running a server. So the last thing I want to do is talk about, what if I want to pull in arbitrary data from the outside that's too large that I'd want to keep all of it at once. I don't want to store it. As it turns out, I gave the demo of the client, gave the demo of the server, but I'd like to show something that's a little taking advantage of that live connection to stream in some useful data. So let me pull in a different script. And this is something that some people use as a metasyntactic variable similar to foo. But in this case, I guarantee you it's actually accurate. I need to run the server again. So let's stream in some data repeatedly and do something useful with it. Live video streaming into a pre-OS environment and playing video a frame at a time via EFI and Python without an OS. Now, I would suggest that we're unlikely to ever have the audio interfaces, but if history has shown me anything, then somebody's probably going to implement it, and it might be us. And with that, I'm happy to take questions. Let's see. I think there's a couple of mics in the room.
Yeah, hello. Yeah, thanks, Josh. If you have questions, just point, and I'm going to come.
Do you have plans for IPv6 support?
Do I have plans for what support, I'm sorry? IPv6, yes, absolutely. That is probably the biggest thing that is missing from this that we know people will actively want to use. That, and the other big one is DNS for name resolution. So there's a reason I was using IPs for everything. Turns out that's handy in a test lab anyway, so it's not a big deal. But the reason we haven't done that in particular is not because there aren't interfaces to it. There is an interface provided for DNS resolution. No BIOS actually provides that interface, which means in practice we're going to need to go implement DNS ourselves and go make a connection to the DNS server, pull that out of the DHCP request, do it by hand. So that'll come later. But IPv6, there are interfaces. Most BIOSes do provide them, and that is on the list as soon as we run into a case where we need it, and we probably will. Other questions?
So it seems like you spent a lot of effort.
Hello.
So it seems like you spent a lot of effort to turn an inherently asynchronous networking system into a synchronous one. Was there any special reason or advantage to that? Because
So I can actually answer that one pretty easily. So it's not that we turned it into a purely synchronous system. It's we turned it into a system that has the different API style of POSIX and Berkeley sockets. We did not make it 100% synchronous. All of the demos I gave were synchronous just because I'm pulling down data or pushing out data, and I expect that to be something I'm waiting on. But we actually do implement the socket set timeout or set blocking methods. You can set the socket to non-blocking, and in that case, if you try to receive, it will tell you you don't have any data yet and return and timeout, and you can call select to see if you have data. So if you wanted to build a fully asynchronous server with a stack of sockets that all have asynchronous timeout set and non-blocking mode set, call select on them and see what you do. If I were willing to type in a whole bunch more for a demo, I actually have a multi-user chat server that works just fine. Take in data, send to all sockets. So yes, it's fully asynchronous. It's just I was using synchronous capability. The EFI interface, you would typically set up the callback and then spin until that callback sets a flag when you want to make it synchronous. In this case, I wanted to support both synchronous and asynchronous modes for the Python sockets module. Other questions?
Yeah, just raise your hand. I guess we don't have any more questions, so thank you very much. Big hand for Josh.